he's trying to get around the corner with his board, and one of his hallways is 4 meters wide and one of the hallways is 3 meters wide. And he has this gigantic 10 meter or 10 foot maybe long board that he wants to go like that. Okay, so we know that at any point, this board has to be able to fit kind of at all of the kind of progressive angles, because the board would start out kind of like this. Oh, I'm going to make it still touch. Because as you started like rotating the board around, you could have the board kind of going like very long down the hallway, and then it would start like tipping more, and you want it to be able to like tip more down that hallway like that, kind of like progressively get it around the corner. Also with those sound effects. So we have, just kind of going back to square one here, we've got this 3 meters, and we've got this 4 meters, and we've got his board that we want to see if it can fit, if it's 10 meters long. And the thing that's changing here is the angle of where the board is in terms of the wall that he's kind of coming from and curving around, right? It's going to like curve around and eventually get over to the other side. So what I want to do is take a look at his board as 2 different pieces. So I'm going to look at this as how much of the board is like in the first hallway, and we can call that X, and how much of the board is in the second hallway, and we can call that Y. So there we've got kind of dividing that total length up into an X amount and a Y amount. So if we want to figure out what X and Y are, I'm going to put 2 triangles here and relate X and Y in terms of theta. Hopefully we're okay with kind of seeing that this would be similar triangles, and that's also theta in there. Okay, so now we have 2 triangles. We've got this is theta, and that would be Y. I'm going to label the 3 meters over there because it's the same as where that would be. And the other triangle, we have 4 meters here, and theta would be there, and X is there. We okay? Can everybody see that? So what we want to do is figure out what we would have here in terms of each piece. So how long is X in terms of theta, and how long is Y in terms of theta? So for the X, I have 4 is the opposite and X is hypotenuse. So I have sine theta is 4 over X. So X is 4 over sine theta. And I'm going to write that as 4 sine theta to the -1 because I kind of see chain rule coming here. And then I'm going to do the same for the Y, but here I have 3 as the adjacent and Y is the hypotenuse. So I'm going to have cos theta is 3 over Y. So Y is 3 over cos theta. And Y I'm going to write as 3 times cos theta to the -1. So that's kind of what I'm left with. This is where it gets a little tricky to multitask. So I had X was 4 sine theta to the -1, and Y was 3 cos theta to the -1. Is that right? Okay. So my total length, the amount of length that can fit, is going to be these two things added together. 4 sine theta to the negative 1 plus 3 times cos theta to the negative 1. And then we're just going to do the derivative. And the derivative here is going to involve chain rule on these trig functions. So L prime at theta, because the length is a function, the maximum length is a function of what the angle is there. We'd have negative 4 times sine theta to the exponent negative 2 times the derivative of the inside stuff, and the derivative of sine theta is cos theta. And then I have minus 3 cos theta to the negative 2 times the derivative of cos theta, which is negative sine theta. And then simplifying this, cleaning it up, I get negative 4 cos theta over sine squared theta plus 3 sine theta over cos squared theta. And if I want to find where the derivative equals 0, I think I'm going to actually have an easier time bringing the 4 cos theta over sine squared to the other side. So I'm going to go up here, and I'm going to say that 4 cos theta over sine squared theta equals 3 sine theta over cos squared theta, and cross multiply here. So there are other ways to solve it. You could get a common denominator and end up with kind of simplifying that fraction. But if I have two fractions added or subtracted equals 0, making them equal to 0 and just cross multiplying is not a bad plan. So here I get 4 cos cubed theta equals 3 sine cubed theta. And there's different ways to solve when you have a relationship between sine and cos, but I think the easiest in a lot of cases would be to divide out the cos and make it a tan, because we've got cos cubed and sine cubed, and we don't have identities for that. But if I divide by cos cubed theta, and I'm actually going to divide by 3 as well. So there the 3's will cancel out, and here the cos cubes will cancel out. So I get 4/3 equals tan cubed theta. So then tan theta is the cubed root of 4/3. Okay, so the cubed root of 4/3, and then do inverse tan. I'm going to peek at the solutions so I don't have to do calculator. You would do, I'll show that step. So you're going to do inverse tan on the cubed root of 4/3, and we get theta is about 0.83327. And make sure you're using radians. Okay. For all calculus stuff, when you're doing trig in calculus, you have to have your calculator in radians. Okay. So then we would go back and test the length. So we said that L at theta, I'm going to add this in. So this was equal to 4 sine theta to the negative 1 plus 3 cos theta to the negative 1. So then we're going to do the length and double check what it is at 0.83327. And I am just going to trust you guys to do that on your calculators. But if you put 0.83327 and do 4 divided by sine of that plus 3 divided by cos of that, you get about 9.87 meters. So he can't quite fit that board around the corner. He'd have to cut a little bit off. Okay? So that's how you'd solve that one, kind of breaking it up. It is like an interesting problem to be able to take a look at dividing something into two pieces and doing it in terms of angles. Optimization problems with trig aren't as common, but for sure they can happen. Okay. Another good one to look at here would be the question where it was like the guy canoeing and then running down the beach, and there was a second video for that showing how you could solve that same question, not how I did in the lesson if you guys stayed online for that lesson, but using like what angle should he aim, okay, down the beach. So that's also another good application for trig.